Okay, so now that we are live, I would like to welcome everyone for this last quantum matter seminar of this term. We will have a break now, and this last seminar should be special because we have now Tais with us from Iowa State University. She's going to talk about how we can tune magnetic symmetries and topology using bicircular light. Thank you very much, Tais, for coming today, for giving the seminar to us. And feel free to start whenever you want.
Thank you very much, Chrisia, and thank you for the invitation. I'm very happy to be here. And so I'm a postdoc at Iowa State University and in its laboratory. And today I'm very happy to share with you some results of my most recent project, where we investigated how to use this very particular type of light, the bicircular light, to manipulate symmetries and topology in materials. So we are going to see in more details during the talk that this bicircular light is a combination of circularly polarized light that gives rise to this rose pattern that you can see here. And this rose pattern is very interesting because it can break several symmetries that only a circularly polarized light or only a linear polarized light cannot break. So we have more control on the symmetries. And since there is this connection between symmetry and topology, we can also have more control about topological properties. And we can do very exotic things with this light. So, and I forgot to say more details about what we're going to see here today. You can check in this paper listed here. So before I start, I would like to acknowledge the people that are involved in this work. My supervisor, Professor Peter Ort at Iowa State University, and our external collaborators, Professor Robert Janislager. He was a postdoc at Harvard, now he's in University of Cambridge, and Professor Oli and his postdoc at the time, Pablo, that are in Argon Lab. So what I thought, the way I thought to organize this talk for today is I'm going to start with a brief introduction to motivate the topic of this talk. So why is it so interesting to use light to tune properties of material? Why does it work? And then I'm going to tell you a little bit more about what is this bicircular light that has been not so much explored up to this date. Then I'm going to move to the principal body of the talk, that is to see what is the effect of this bicircular light into two topological phases of matter. One is Dirac semimetal, and the other one is topological insulator. So if you have questions, please interrupt me at any time. Okay. So let's start with a brief introduction. So the basic concept that will be involved in this talk is the use of a strong coherent light pulse to tune properties of materials. So the basic idea is that we have a material in equilibrium here, illustrated by this gray box, and we are going to shine into this material a light pulse. This light pulse will drive the system out of equilibrium, and several things can happen. We can have, this light can dress the electronic bands, and this can drive the system through several phase transitions. We can also have the emergence of new phenomena that has no counterpart in equilibrium. And as we're going to see in more details in this talk, we can even use this light pulse to realize phases of matter that are really, really rare to find in equilibrium. So of course, that the output of this interaction between light and matter depend on the characteristics of this light pulse that we choose to use. So it will depend on the incidence direction of the light or polarization, the intensity or fluence of the light and frequency and so on. And an important parameter that we can tune in the light pulse is the frequency. And we can always choose the frequency to match the energy scale that is relevant for the system that we want to drive. So there are many different things that we can do. So for example, let's suppose that we are going to choose a light pulse that has frequencies of terahertz. So in this case, what can happen is that the light, if we shine this light into a solid, this light can couple directly with the phonomodes of the solid, and this can introduce deformations in the solid. I can activate some phonomodes that will distort this lattice so we can design the light field to produce the deformations as we want, like to change the material on demand. And these deformations will be felt by the electronic degrees of freedom, and we can drive phase transitions by doing this. This is a field of research that is known as non-linear photonics. Now, if we increase the light frequency a bit more to mid-infrared and infrared range, we can now couple directly the light with the electronic degrees of freedom. And if we do this, we can change the electronic hoppings in a lattice. For example, we can modulate these hoppings, or even, as we're going to see, introduce new hoppings. And we can also change the electronic Bloch wave function. So we can make, for example, a material that was topologically trivial to become topologically non-trivial by modulating its Berry curvature in the presence of a light field. If we, all these phenomena that we saw here, they are usually very short-lived. They will only take place during the time that the light pulse is on. And after we switch off the light pulse, the system will relax back to equilibrium. But sometimes, if we use light frequencies even higher than infrared, we can introduce metastable states. So imagine that we have a system that in equilibrium is trapped in a global minimum of its free energy landscape. And now when we shine a light into this system, we are going to drive it out of this minimum, and the system can get trapped in a nearby minimum. And as long as this energy barrier is high enough, the system can stay trapped in this other minimum for quite some time after the pulse is off, like in the time scales of days, for example. So this is how it's also possible to light induce metastable states in the systems. In this talk, I would like to focus in the frequency range, in this frequency range. And the technique that we are going to explore is called Floquet engineering. So let me tell you a brief introduction about what is Floquet engineering. So this is a very popular technique in condensed matter physics in the last few years to control properties of materials. And every time that you read or you listen about Floquet engineering, the first thing that has to come into your mind is that what we are doing is that we are coupling the system to an external periodic perturbation. So in the specific case of this talk, this external perturbation is a light field. So we are coupling a given system that we can choose with a periodic light field. So what does it do? What does it do to the system? So as a simple example to understand this technique, let's consider a chain, as you can see here, a unidimensional chain. In equilibrium, it's described by a Hamiltonian H, and the electrons can hop from one side to the other with hopping amplitude that I call J. Now, we shine to this system a periodic light with frequency omega, and as a consequence, our Hamiltonian now will acquire explicit time dependence. It's not a generic time dependence, but it's rather a periodical one, because the Hamiltonian now acquires the same periodicity of the light field that we are driving the system. So solving this Hamiltonian now is very similar to find the Bloch states in a crystal. In the crystal, we have periodicity in space. Here, we have periodicity in time. So how we can interpret this time-dependent problem now is the following way. We have, in the presence of the light field, infinite copies of our original 1D chain. Each of these copies are modified by the light, and they are also coupled by the light field. So electrons in each copy that we call each Floquet sector, they can hop within the copy, but they can also have virtual hoppings to other copies, other Floquet sectors that I have represented here by, for example, J2, J3, and J4. And what happens is, if we increase the frequency of the light field, these copies will become less and less coupled. And in the limit where this frequency exceeds the characteristic energy scale of the problem in equilibrium, that is the hopping J in this case, we can treat this system perturbatively, and we can integrate out all these other copies and be left in the end with, again, a single 1D chain, but that now has properties that are potentially very different from the original problem in equilibrium. So this effective 1D problem will now be described by an effective static Hamiltonian that encodes all the characteristics of this light field that we use in the drive. And the electrons here in this effective problem, they will have hopping, like near neighbor hoppings that are modified by the light, they are dressed by the light. But we also have emergent hoppings that are between nearest neighbors, for example. So the physics of the electrons in this effective problem can be very different from the physics in the original problem. And then we can use this to tune the physical properties of the system on demand. We can choose the frequency or the polarization or the incidence direction of this light field to choose what physics we want to have in this effective problem. Because by choosing this light parameters, we can tune these hoppings here. This is a very powerful technique, but it also has some challenges that it needs to overcome. And so, as we saw before, when we irradiate a light field in the system will evolve from the original equilibrium state that is represented here to a new steady state that is described by the effective Floquet Hamiltonian. But while the light is shining on the system is also absorbing energy from this light field. So the existence of this new steady state is not guaranteed. It can be destroyed by heating effects. So it has to be analyzed case by case if this state can indeed exist. So this is one challenge that happens in all Floquet engineered systems. And another complication is, as I said before, is that this steady state that we might have in the presence of the light is very short-lived. So after the duration of this pulse, the system will eventually relax back to the original equilibrium state. And this relaxation is often very fast, which makes it very challenging to detect this state, this steady state that we create. But besides all of these complications, there were some successful measurements. So the Floquet states were measured for the first time in the surface of this material, the bismuth selenide, a couple years ago in 2016. So bismuth selenide is a topological insulator, meaning that in the surfaces, meaning that in the bulk we have gapped bands, but in the surfaces we have metallic states, metallic states that forms a Dirac cone, as you can see in this picture here. So without the light, if you choose one surface of the material, any surface, because it is a strong topological insulator, you will see this Dirac cone forming here. So this was I forgot to say, but this was observed with time resolved arcs. So without the field, you see the Dirac cone. Now we turn on the light field, and what you see here in the presence of the light is a dispersion that is very different from the single Dirac cone. What you can see here is actually some repetitions, some replicas of these Dirac cones. And these are the different Floquet sectors that we saw in the example in the previous slide. But now, since once the light field is gone, you go back to this Dirac cone here. But the fact that we could observe these Floquet bands here, these replicas of the Dirac cones, shown that Floquet, we can indeed use Floquet theory in real life. But perhaps one of the most recognized examples of Floquet engineering is the light-induced anomalous Hall effect in graphene. This was cover of Nature Physics 2 years ago. So the idea is the following. So in equilibrium, in graphene, we know very well that electrons will hop in a honeycomb lattice. this system will have a dispersion that forms Dirac cones as illustrated here in the points K and K prime of the Brillouin zone. But now, if we shine to the system a circular polarized light perpendicular to graphene plane, what happens is that light will change this first neighbor hopping, but we'll also introduce an entirely new hop in the system that is this second neighbor hopping that is now imaginary hopping. And then, as a consequence, graphene in the presence of the circularly polarized light mimics exactly the Haldane model. So what does it mean? As a consequence of this complex hopping here, the dispersion will not have a Dirac cone at K and K prime anymore. This Dirac cone will be gapped out by the light, as you can see here. But this opening of the gap is a topological gap opening, in the sense that the valence in the conduction band will acquire a finite Berry curvature that, when you integrate it in the entire Brillouin zone, will give you a finite Chern number. And as a consequence of having this finite Chern number, the material is now a topological insulator. And it will have then in the edges of this 2D graphene layer, it will have edge states whose quantization, whose conductivity is quantized to integer number of integer multiple of E square over H. To be more precise, the multiple here is 2. The quantization is 2. And this could be observed experimentally. So here is a plot of the conductivity as function of energy for this material in the presence of light. So this is the fluence of the light. And you see here that you have this plateau where the conductivity is very close to 2. So I see that someone has a hand raised. So do you have a question?
Do you mind if I ask a question?
Of course, please.
Okay. So this is Sang Chong at Rutgers University. So in terms of symmetry, circular polarized light basically has the same symmetry with magnetization. So I believe illumination of a circular polarized light on any materials, even glass, piece of glass, can induce magnetization. In fact, may be very small, so that their magnetization can induce this so-called anomalous Hall effect in the plane.
Yes.
So, of course, so the effect can be big, larger in certain systems like a graphene, but in general, this should be working for any materials, including, amorphous materials.
Of course, yes. Because it breaks time reversal, as you said. So you break time reversal, you have an effective magnetic field in the system.
Correct.
Yes.
Okay, so you agree on that. Okay, good. Yes. Very good. Okay, thank you.
You're welcome. Okay, so so the fact that we could observe, that they could observe this quantization is a very successful proof that Floquet engineering can be used to tune material. There are many other examples of where this technique were applied. So, for example, Floquet engineering was also used to induce topological states in twisted bilayer graphene. There is also works on light-induced superconductivity and so on. But here we are going to be focused in using Floquet engineering to tune states that are already topological in equilibrium. So the goal is that we want to design a light field that we can use to dynamically tune topological properties of materials by dynamically controlling the symmetries of the system. So we are going to focus into 2 classes of topological materials. One of these classes are Dirac semimetals. And just for the audience to be sure that we are in the same page, when I say Dirac semimetals, what I mean are 3D materials that in the bulk bands, they have some nodes like this, where the valence and the conduction bands, they touch linearly, so they form locally this Dirac cones dispersion. And these nodes are, in general, close to the Fermi level. So if you wish, you can call these materials an analog of a 3D analog of graphene. So for this direct semimetal phase to exist, it's very important that we have time reversal and inversion symmetry. And this is a phase of matter that is protected by crystal symmetries. So we need, for example, rotation symmetry to avoid that the valence and conduction bands hybridizes and open a gap at this point. So because of these two symmetries, we have a Kramer's theorem, right? And then at this point here, this node that is called Dirac node is fourfold degenerate. So what happens now if we break one of these symmetries? In particular, what if we apply a circularly polarized light to, again, break time reversal symmetry? In this case, it was shown theoretically that a circularly polarized light, when shined into the system, will split this Dirac cone into two other cones that are now called biocones. These points where the valence and conduction band they cross, they are now called bionodes, and they are twofold degenerate. And here they are not protected by symmetry, but they are protected by topology, which is a strong protection in the sense that these cones, these bionodes, they always come in pairs. And if you want to get rid of them, you have to annihilate one with the other. So now the question is it also possible to design a light field that can break at the same time reversal symmetry and inversion symmetry, so we can, besides separating this cone in momentum, also separate these cones in energy? Because here, since we have inversion symmetry enforces us to have these two biocones at the same position. Now, we would like to have them isolated because there are interesting transport effects that happens when this is the case. So the question is, can we do this with light? And the answer is yes. And for this, we need to use this very special type of light that is bicircular light. And we are going to see this in details in this talk. The second class of material that we are going to study is topological. It's a topological insulator. So now, instead of having a crossing like this, we have another question by Professor Sun.
Yeah, sorry to keep interrupting you.
That's fine.
I want to make sure about this one. So I think you're talking about I times T. This product symmetry is broken. Rather, I mean the right-hand side in the cartoon.
Here, you mean?
Yeah, that's the one having not just I broken and T broken, but I think I times T is broken.
Could be, but I want to break each one of them separately.
No, I think if you break I, if you break T, but if you, still, if they are broken in the same way, then I times T is not broken. In that case, you do not have this case.
Of course, so, yeah, but
so what is important is I times T should be broken.
It will be. It will be.
So I broken is not enough. I times T should be broken.
Yes, it will be broken. I'm just saying this is not necessarily the case, right? I can have cases where I break each of them separately, but I still have the product of time reversal and inversion. Here, I'm going to break both of them and also the product of them.
Okay, good. Okay? Yeah, I want to make sure. Thank you.
Okay, you're welcome. So, so as I was saying, we also want to look to topological insulators. In this case, we have a gap in the bulk bands, but in the surfaces, we have metallic states that are protected by topology. And the idea here is what happens to this topological state if we apply now a bicircular light into this system. And we are going to see that we can induce even more exotic gapped topological phases in these systems that are very, very rare to find in equilibrium. Okay, so let's start with the case of the Dirac semimetals. So the formalism that we are going to see here today is generic, and you can apply it to any Dirac semimetal that you want. But for showing concrete results, I'm sorry, I got a bit ahead of myself. So before I go to the Dirac semimetal, let me tell you about this light, right? Because I have been talking a lot about BCL, bicircular light, but I never formally introduced it. So what is this bicircular light? So as I mentioned in the beginning of the talk, this is a linear combination of two circularly polarized lights. So I have here one light that is polarized to the left, shown in purple. It has frequency omega. And I have another light that is circularly polarized to the right with another frequency n omega, where n is chosen to be an integer. And this is so because then the result of this superposition will also be periodic. Okay, and we also have this same frequency omega. So what is the result of this combination? This is a rose curve like this. So the rose curve will have n+1 fold symmetry. And since each of the circularly polarized light has a chirality, this combination also has a chirality, so it breaks time reversal symmetry in the same way that the circular polarized light does. But because of this spatial pattern that we have in the electric field, it also breaks crystal symmetries of the system. So I can, for example, choose, sorry, let me go back. So for example, if I look to this pattern here, it's clear that it will break this mirror at x. So we cannot have y going to minus y is not a symmetry of the system anymore. It also breaks, for example, four-fold rotation. But a light like this would preserve three-fold rotation because it's a three-fold symmetric rose. We can choose different ends. And by doing this, we change the shape of this rose. For example, if we change n equals 3, we have a rose that is four-fold symmetric, like this. We can choose five-fold symmetric, and so on. So different ends that we choose will give us different patterns. And as a consequence, this can break different crystal symmetries. Another possibility that we can do is to introduce a phase difference between these two circularly polarized lights. And what this phase difference that I called here alpha will do, it will promote a rigid rotation of this pattern. So if alpha equals 0, no phase difference, you'll see this curve in blue. If I have now a phase difference of pi/2, this pattern is rotated by pi/2. And then by rotating the pattern, I can again break different symmetries of the system. So from this figure alone, you can already see why this light is very interesting. You can break symmetries that with circularly polarized light you cannot break. For example, you can break simultaneously time reversal symmetry and inversion symmetry of this light. And this will have very important implications for the rest of the talk. So with this type of light, we can have more control of the symmetries of the system because we have much more tuning knobs, we have frequency, we have multiplicity of the frequency, we have phase difference and so on. And so we have enhanced control of the system symmetries. So let's see now what is the effect of this light in a Dirac semimetal. And as I was saying before, the formalism that you are going to see here today can be applied to any Dirac semimetal that you want. But for concrete results that I'm going to show, I chose in particular cardiomyocyte. And the reason is because this is a very well-established Dirac semimetal. It's a material that is of great interest for our group. We have collaborators that can produce very high quality samples of this material. And we have plans of, some collaborators have plans of starting to do this experimentally to test our predictions. So that's why we wanted to show results specifically for this material. So let me just tell you a little bit about some properties of cardiomyocyte. So in terms of crystallographic structure, this is a very complicated material. It's a tetragonal crystal structure. It has more than 40 atoms per unit cell. You can see the unit cell here. And the band structure was calculated by first principles by DFT and shown here. But what is important for you to focus is into this band close to the gamma point. Here we have an inversion of bands that are majoritarily composed by 5s orbitals of cadmium and 4p orbitals of arsenide. And this band inversion will cause the crossing of the valence and conduction band that originates the Dirac cone here. So if we zoom into this region, we see a Dirac cone that is illustrated here. In this material, There are two of them, one in the positive part of the KZ axis, the other one in the negative part. So these cones are along gamma Z direction. And as I said before, a Dirac semimetal needs crystallographic crystal symmetry to be protected. In this case of cardiomyocyte, the symmetry is fourfold rotation along this Z-axis where the cones are. And these Dirac cones, they were observed by artists, okay? Okay, so another thing that is important is that these topological bands here that are highlighted here, they are very well separated from other trivial bands of the material. And as a consequence, although the material is very complicated and has a lot of bands, we can describe the topological properties by a minimal four-band model. And so this is the basic model that I'm going to consider in the remaining of this talk. So let me just introduce you a bit about the model. So as I said, cardiomyocyte can be described by a minimal four-band model around the gamma point. The model is shown here. Don't worry too much about the expression for these coefficients. They are just expansions, they are polynomials of momentum that are valid along the close to the gamma point. And the sigmas and taus, they are polymatrices in spin and orbital space. If you diagonalize this Hamiltonian, this is the band structure you find, and a cut along the KZ direction give you this band structure. You can clearly see the two direct cones here. Remember that in equilibrium, this system has inversion and time reversal symmetry, so each band that you see here are twofold degenerate, okay? Now we are ready to apply the light here and see what is the effect of this light in the band structure. So how our bicircular light is going to change this band structure and how it's going to change the electronic properties of the system. So let me show you step by step how this coupling works and how Floquet engineering of this system works. So as we saw before in the example, we start with the system in equilibrium. So we have here the Dirac semimetal that is described by this Hamiltonian minimal K.P Hamiltonian H of K. And we are going to couple the system with the bicircular light. The way we couple the system is through minimal coupling. So we go back to this Hamiltonian. Everywhere we have K, we replace by K plus A. And now, when we do this, we have a Hamiltonian that is periodic in time because of the periodicity of the vector potential here. And now, if we choose the frequency of this light to be much larger than this typical energy scale here that are called Lipschitz transitions, so Lipschitz energy. So in this energy scale, the bands of the Fermi surface of the system in equilibrium change from electron pocket to 2 points, due to the Dirac cones, to whole pocket. So that's why it's called Lipschitz energy. So if I choose a frequency that is much larger than this Lipschitz energy, I will not have coherent excitations of electrons because I will not be coupling these two bands. And I can make a perturbation theory in the inverse of this frequency. Is the same perturbation theory that I mentioned in the beginning. It's called high frequency expansion. And I can go from this time-dependent Hamiltonian here to an effective Hamiltonian that is very different from the one that we have in equilibrium and that is time-independent. So if I truncate this expansion in linear order in 1 of omega, this is what I find, this Hamiltonian here. It has two contributions. One term here is just the time average of the time-dependent Hamiltonian over one light period. And this term doesn't do much for us. So basically what it does is just to dress the original bands without breaking any symmetries. And the only thing that will happen is that we are going to have a relocation of the Dirac cones. So we are going to shift the original Dirac cones to new positions, as you can see here. So dashed line is before the light, solid line is after the light. You have to be careful though, because if we choose a light field that is very strong, so if we increase the magnitude of A of t, what can happen is that we can get rid of these two cones here. We can have a situation like this where the band inversion is completely unknown, and we don't want it to happen. So we have to keep in mind that we have to choose a light field that is not very strong, so a situation like this doesn't happen. And we have now the second term here, and these are the new terms of the model that are not present in the equilibrium Hamiltonian. And these are the new terms that are induced by the light field. If you want to think back in real space formalism, this is the term that will be related to the new Hawkins that appear in the presence of the light field. And these terms will be the ones that will lift the degeneracy of these bands. These terms will break several symmetries that we had in the problem in equilibrium. And all the features of the light, for example, incidence direction, phase difference, frequency, it will all be encoded in this term here. And this is the term that ultimately for us in our model will drive different topological transitions. So let's see one example of what these terms do. So remember that for bicircular light, we have several tuning knobs, right? We have incidence direction of the light field, we have frequency, we have amplitude of the vector potential or the fluence of the light, we have phase difference and so on. So let's fix for now the incidence direction. We are going to choose the bicircular light to be perpendicular to this 112 surface of the material. It is represented in blue here. And why this surface? This is just because this is the surface of cardiomyocyte that is naturally exposed when you grow the material. So this is the surface that the experiments can look. And let's also fix the frequency of the light should be again in this range that is very larger than the Lifshitz energy, and fix also the phase. Okay, so I pick here the phase to be pi/2. This is the spectrum of the effective Hamiltonian that I find. So first thing that you can see is because we broke time reversal symmetry, each of the Dirac cones that we had before is split into these two Weyl cones. You see two here and two here. Now, depending on the alpha that I choose, and you can see this in this table, I can have different symmetries for this band. So for example, if I choose alpha to be 0, I have this symmetry that is a combination of mirror and time reversal, and it would enforce these cones in blue and green to be pinned at the same energy, and the same thing for the red and the purple. But if I choose alpha to be anything that is other than 0 or pi, these cones are now either completely unrelated by symmetry because all the symmetries can be broken, or they are mapped into itself, so they can in general occur at different positions and different energies. And we can see that this is exactly the case when I choose alpha to be pi/2. If I zoom into this dispersion, and you can see the zooms here, you see that the cone in red and the cone in purple, they are at different energies, the same for the ones in blue and green. Of course, that here the energy difference is very, very small. It can be controlled, like you can make it larger if you use a field that is more intense, or if you decrease a little bit the frequency of the field. But because in cardiomyocyte, the cones in equilibrium are already very close to each other, you cannot make the separation much, much bigger than you can see here. But in other materials where these cones are more separate from each other, you can increase the separation even more. Okay? So you can see that bicircular light can achieve that situation that we wanted in the beginning, that is separating these Weyl cones completely in energy and momentum. And this is very interesting because now we can relax this condition that alpha was fixed and see what are the ways that we can tune these 4 Weyl cones. And there are 2 effects that appear in the presence of this light that we don't have analogs in the presence of other types of light. The first of them is the control of the position of these direct nodes in momentum space. So here I'm showing to you the position of the 4 bio nodes in momentum space as function of alpha. So as a vary alpha from 0 to 2 pi, each cone performs a loop in momentum space, as you can see here. So I'm using the same color code as before. So the cone in red is shown, the cone in red makes this loop in red, the cone in blue makes this loop in blue, and so on. And if I increase the amplitude of my light field, I also increase the size of these loops. Why is this interesting? It's interesting because if I keep increasing the size of this loop, I can reach a situation where I can braid 2 of these cones. So that I represent here schematically in this picture. So I can have, for a given alpha 1, I can have 3 of my cones that are separate, but if I change alpha, I can change position of 2 of these cones. And this opens the possibility for a light-induced type of topological phases that is called Euler class of materials. So in this Euler class of materials, when you have this braiding of bio cones, you can no longer annihilate cones that before had a chirality, a net chirality that was 0, because this braiding changed the chirality of the cone, loosely speaking. In cardiomyocyte, unfortunately, we annihilate the cones before this braiding takes place, but it's an interesting direction in the future to analyze if this regime can be achieved in other direct semimetals. This is still an open question. So another effect that is very interesting and very promising is that we can, with bicircular light, we can have a dynamical control of transport properties in biosemimetals. So I showed you before that we can control the position of the biocones by changing the phase difference in the bicircular line, but we can also control the energy of the nodes. So here I zoom in into these 2 cones in red and in purple, and I show in this panel here the energy of each of these nodes as function of alpha. So you see that as I change alpha from 0 to 2 pi, this energy oscillates, right? And if I have 0 or pi or 2 pi, this energy is the same for the red and the purple. This is because of the mirror symmetry that I mentioned, and the energy is different for all other values of pi, but it is always modulated by pi. Why is this interesting? This is interesting because there is an effect that is called gyrotropic magnetic effect that happens if I apply to the system an extra external magnetic field. So this magnetic field has to be time dependent, so oscillating field, but if a frequency that is very, very small in comparison to the energy scales of the transitions that I can have. And if I do this to my system, it will respond with a current that is linearly dependent on the energy separation of these nodes and also on the magnitude of the magnetic field, okay? This is a property that is related to the Fermi surface of the material. So it's not a topological current in a sense. But if you remember before, since we can tune this energy separation with the phase difference of the bicircular light, we can also tune the value of J. So this current will have the same modulation that the energy of the dark cones, of the biocones had. And then we can change the value of this current by changing alpha from 0 to 2 pi. And what is interesting is that this periodicity on the gyrotropic magnetic current is going to be there in your system no matter if I have heating or not, right? Even though I have heating effects that it's very hard to avoid, this periodicity will still be there and can still be measured experimentally. So this shows us that bicircular light enables a dynamic control of the gyrotropic magnetic effect which is not possible with other types of light.
Can I ask a question on that point?
Okay, so
Can I ask a quick question
that's
on that point?
what bicircular light can do with Dirac semimetals. But
we have a
sorry,
question.
I don't think I can hear you. Sorry, just a second. I
We
think I
have a
some
question.
problem here.
Mhm.
Yeah, I wanted to ask a
Just
question.
one second. I have some problem in my. Let me just.
Can you hear?
Let me no. Let me stop share for a second. I think I have some problem here in my audio. Sorry. Okay, my phone got disconnected. I think it's back now.
Okay, are you able to hear me?
Yes, I can hear you now.
Okay, great. Yeah, I wanted to ask a question about this
Sure.
gyrotropic effect. You said that it was
Yes.
very insensitive to heating. What is
Yes.
the reason that it doesn't care about the heating effect in the system?
So the reason is because what is most important for this modulation that you see here is this energy separation of the cones and the modulation of this energy separation. So even though we can have heating in the system, like the heating won't change this modulation. You cannot change this the period of this current.
Well, okay,
So-
it would change the period maybe, but what about the I guess the amplitude would depend on the heating.
That's true. This could happen, yes, but so the idea is the following. So the idea is that you can have your system and you can apply a train of DCL pulses if you want. And for each case, the idea is to measure the current and dividing by magnetic field, for example. And if you keep track of it, you are going to see the period.
Right. Okay. I guess what I'm thinking,
Mhm.
what is the amount of information that you can get by seeing this period in alpha? Like imagine that you had some like higher order Weil points.
Okay.
Then is the period modulated in some way?
Good question. It could be because, for example, when you calculate this current, it is very important that you have this linear dispersion here.
Mhm.
I don't know what happens with higher order nodes, like you had, for example, an extra parabolic band here, right, touching this point. Could be that the shape would be different, but the idea here is that if you detect a modulation like this is a way for you to diagnose the presence of these Weil nodes in the bulk. So in a sense, this is a novel transport property that would indicate that you have a Weil node in your system or more than one Weil node in your system.
Okay. Like I guess imagine, like I guess
Mhm.
I'm thinking of the chiral charge at the Weil nodes. Like let's imagine
Yeah.
that you have like two that are on top of each other. So it's like chiral
Right.
charge 2 rather than 1. Then how does that affect this amplitude or the periodicity in alpha?
I think it would. I think like without making any calculation, it could give a constant factor on top of what you are seeing here, because what you don't see in this expression is that what enters here is chirality of this cone minus chirality of this cone, and they have opposite chirality, so they add up. So if I had here, for example, chirality 2 and chirality 1, let's say, I would have a factor of 1. If I had 1 and minus 1, I have a factor of 2 that is already inside this expression. So you would change the magnitude, the overall magnitude of J, but not the period, because still you would have this delta E modulated by alpha.
Okay. So in principle, it's a way to also diagnose like what type of Weil system you have. So not just that you have a Weil
Yes.
system with nodes at different energy, but you might be able to diagnose the chirality of the nodes.
Could be, but I think this would be a little bit more difficult because you would have to have precision about the magnitude of this current, right?
Yeah.
Which also depend on the magnitude of the field, and as like depends also if you have disorder or not. Like this requires that your sample is very clean, for example. So I think it would be much more difficult to diagnose chirality than to diagnose the presence of the nodes itself.
Okay.
Okay.
Great. Thank you so much.
You're welcome. Okay, so anybody else has questions now that I can hear? Okay, then I think I'll just move forward. So we saw so far what is the effect of this bicircular light in Dirac semimetal, but it was also realized a couple years ago that if you take bulk cardiomyocyte and you keep decreasing the thickness of this of cardiomyocyte until you make thin films, you can, in this limit of thin film, has quantized conductivity again. So you have quantum anomalous Hall effect in cardiomyocyte. And this was investigated by several groups. And what happens when you have these cardiomyocyte thin films is that you need to grow them in the top of a substrate. And the substrate, it naturally induces a strain in your cardiomyocyte film because of lattice mismatch between the two types of crystals. So there is a question that naturally arises in this case, that is, what would be the combined effects of strain and bicircular light in cardiomyocyte? So that's what we investigated next. So the formulas will be the same as I showed you before. Cardiomyocyte will be still described by a minimal model that is almost the same as before, but now we have an extra term here that will describe strain. And what type of strain? It's a uniaxial strain that will break the C4 symmetry that I said before protect our direct nodes. And it also breaks some of the two-fold rotation symmetry that the system had before. So if I'm breaking C4, now I can hybridize conduction and valence band. And as a consequence, you see that the direct nodes that we had here before disappear. So I open a gap in the system. And again, this is a topological gap opening because the system, when you apply strain, goes from direct semimetal to a strong topological insulator. And as a characteristic of strong topological insulator, any surface of the material that I look, I'm going to see surface states, and I'm going to find that the surface states are Dirac cones. So as a general rule, in each surface of the material, I'm going to have an odd number of these Dirac cones that are pinned to these time reversal invariant points of the surface. Here, for example, the Dirac cone is pinned to the gamma point of the surface. This is in equilibrium without light. So what happens now if we shine into the system bicircular light? So as before, I'm going to choose a direction. Actually, the same direction as before. I'm going to choose a bicircular light that is normal to this 112 surface. And as we saw before, by applying this light, we can break several of the symmetries that the system initially had. As a consequence, we are going to leave the degeneracy of these bands. So each of these bands break into two, but I still have the gap in the bulk bands here. And you can see that a very interesting situation that can happen is if I choose to dissipate the difference to be pi over 2. And why is this interesting? Because if I look into the symmetries that I enforce in the presence of the light, the only symmetry that remains in the bulk of the material is this combination of two-fold rotation and time reversal symmetry. This is a symmetry that we call generically 2' symmetry. It's a magnetic symmetry. And this is very nice because whenever we have symmetries that in the bulk of the material reverses an odd number of time and spatial coordinates, which is the case of 2', for example, we have ideal conditions to have a magnetic gapped topological phase that is called axion state. So an axion state is a very exotic phase. It's characterized by magnetoelectric coupling in the bulk of the material, which means that if you apply a magnetic field to the material, we are going to induce a polarization, or if you apply electric field, you induce magnetization. And in the case of axion insulator, because of the symmetry here, this magnetoelectric coupling is quantized in the bulk of the material. And this quantization manifests also in the surfaces of the material, because the surfaces that are not metallic, the surfaces that are gapped, they can host half-quantized anomalous Hall effect that are consequence of this quantized magnetoelectric coupling in the bulk. And here, in the case of cardiomyocyte with strain and with bicircular light, we induce a different flavor of axion state. In particular, we induce this magnetic axion state because it's protected by a magnetic symmetry. And what it has, what is unique about this phase is that we have a coexistence of gapped and gapless surface states. So the surface states, the surfaces that breaks the symmetry theta C2 that protects the axion state, they are gapped. So they are just gapped dark cones, as you can see here, as you would find in all surfaces of axion state that is protected by inversion, for example. But surfaces that preserve this magnetic symmetry still have Dirac nodes. But what is different here is that these Dirac nodes no longer has to be in the time reversal invariant points. They can move away from this point. And this is a new class of symmetry protected topological phase that was predicted a couple years ago from Xifeng and Liang Fu. And this can be a pathway to realize this phase. This is very rare to find in equilibrium in materials. So far, there is, and I'll go back to this point, so far there is, as far as I know, one material candidate that can exhibit this phase, but you have the possibility of realizing this phase from a topological insulator, a general topological insulator, if you shine a bicircular light into the system. So as I mentioned, we can, in the surfaces that preserve the symmetry, we have these Dirac cones. They can move away from these time reversal invariant points, and how much they move can be controlled by the frequency of the light, for example. So here I show the magnitude of this displacement from the origin as function of frequency. And you see that the smaller is the frequency, more further away the cones from the origin. And this is like frequency being smaller. Remember that we have this high frequency expansion means that the second part of the effective Hamiltonian has more weight in the total effective Hamiltonian. So as I mentioned, this is a possible realization of a novel class of symmetry protected topological phases that was proposed a couple years ago. And I told you before that this is very rare to find in nature. There is, as far as I know, only one material candidate that can exhibit this phase. And just to briefly talk about it, this material is europium indium arsenide 2. This is a layered material. You can see that you have layers of europium intercalated by blocks of indium and arsenide. And what is nice about this material is that here you have a competition between magnetism and topology. So the blocks of indium and arsenide will give you the bending version that you need for topology. So they will provide you your topological electrons, but the europium layers, they have local moments that order at low temperature. In particular, they order in a very exotic helical states. So each of these layers, the moments order ferromagnetically, but the direction of these moments change from one layer to the other in a helical way, as illustrated here. And in this case, similar to the case with light that I just showed you, the axion insulator state is also protected by a combination of time reversal and two-fold rotation that leaves this helical invariant. So as before, we also have coexistence of gapped and gapless surfaces. So the surface at the top surface, for example, breaks this theta C2 symmetry, and we have gapped Dirac cone, but the side surfaces, one of the side surfaces preserve the symmetry, and we have a Dirac cone that is away from the center of the surface. In the case of this material, the position of these cones can be controlled by an external magnetic field that can further change the symmetries of the materials and then shift this Dirac cone to other side surface. So I guess that's what I wanted to show you. I want to leave you with some take-home messages. I hope that I convinced you that this type of light, the bicircular light, it deserves to be explored more. It's a very versatile type of light that allows us to have much more control about the symmetries of the system, and as a consequence, much more control of what we can do with topology in the system. We have several tuning knobs that we don't have in simple circularly polarized light. So for example, we have this frequency ratio, we have the phase difference, and this gives us great control about the system, enhanced control about the system. We show 2 applications of this bicircular light. We show how to use them to tune Dirac semimetals, and in this case, we can induce from an equilibrium Dirac semimetal a generic vial semimetals where the nodes are separating both energy and momentum. And because of this, we can have dynamic control of a gyrotropic magnetic effect, which is impossible with other type of light, because, for example, the circular polarized light, for example, doesn't break inversion. And for topological insulators, we saw that we can realize a magnetic axion insulator that is very rare to find. So there is a lot of interest of using this type of light in topological insulators. I didn't told you in this talk, but we can also tune the surface states in a Dirac semimetal, the Fermi arcs. So we can change the shape of Fermi arcs with bicircular light and then potentially tune the conductivity in the surface. And there are many other things that we can do with these lights. There are directions that I want to investigate in the future. And I think it's very promising. One of them I briefly mentioned in the talk, that is the possibility of induce with light this Euler class of materials. And the other one is I would like to look to light-induced superconductivity in the presence of bicircular light, because since I can break inversion symmetry, maybe I can induce more exotic type of superconductivity, such as non-centrosymmetric superconductors. And that's it. Thank you very much for your attention, and I'll be happy to answer questions if you have any.
Thank you very much for this beautiful talk. We have our first question by Sambo.
Okay.
Okay. Should I ask a question?
Of course, please.
Okay, good. You're very good. It's a wonderful, very, very interesting talk.
Thank you.
I have a number of questions.
Please.
Let's start from easy one. So in this slide, you show this rose pattern, and there is arrow, the circulation direction. Oh, no.
Sorry.
The top.
This one.
Yes.
Sure.
There is circulation direction. That's probably related with this left or right circular polarized light.
Yes.
Now you combine the 2 light. If one is left, the other one is right. When you combine them, then what happens with this circulation?
You will still have either left or right. Depends on which frequency you choose to be the largest one. So for example,
I see.
So here for this pattern, the frequency of the light that is polarized to the right is larger than the one that is polarized to the left. If I change it, then it will circulate in the other direction.
I see. Okay, very nice. Now, you say you break inversion symmetry as well as time inversion symmetry with this BCL. But this light does have some kind of C3 symmetry, right?
Yes,
C3 symmetry.
it does.
So that if there is any kind of linear response, then probably this inversion symmetry breaking probably doesn't do any because of C3. But since you're talking about some extension, it's a nonlinear process, so probably still it's okay.
Yeah.
You know what I'm trying to say, right?
I do. And can I comment? So I have two comments about. One comment is that for the material that I was considering here, the point group is D4H, so it doesn't have C3 anyway. So the point of considering this threefold symmetric light is to break. So I can break C4, for example. But the system doesn't have C3 to begin with. So I don't think like the fact that the light has C3 is very important here. But
Okay.
what is important here is that it breaks inversion.
Okay, I got that.
Okay.
So in general, inversion symmetry breaking has no direction. However, since you have this pattern, this rose pattern, there is a kind of a direction. And then the time reverse symmetry breaking, basically circular polarized light induces this magnetization, which has also direction. And these two directions are more or less perpendicular to each other, more or less perpendicular to each other. So what this means is, in some sense of what you're trying, the kind of material where this BCL can do something interesting is they are so-called, in terms of symmetry list, off-diagonal linear ME system, linear magnetoelectric system. It's off-diagonal because they're perpendicular to each other, this
Right.
and that. So it's off-diagonal linear ME system can be kind of relevant materials for BCL. In fact, 2', you mentioned the 2' is off-diagonal linear ME system, magnetoelectric system, 2'. And so I guess you discuss all these topological materials, why semi-metal, but okay, I have two questions. One is so in general, off-diagonal linear ME system, what BCL can do, have you thought about that?
I didn't in details, in the sense that I never calculate linear and nonlinear response. I only looked to how this light will dress the bands. But it's something that I plan to do. And this is, of course, this is something that will depend like case by case, right? In the system that in the symmetries that I have in equilibrium. For example, in this case that I studied, the point group symmetry in equilibrium was D4H. So from D4H, when you apply BCL, you can enforce a certain subgroup of the magnetic group that is generated from D4H. So if I have a material that in equilibrium belong to another point group symmetry, then I have to do similar analysis to see what are the magnetic symmetries that I can generate with BCL. Okay. And then sorry, go ahead.
No, I just want to say, you may consider, in general, there are many off-diagonal linear ME systems where these two directions are perpendicular to each other. You apply electric field and then you get magnetization, but they're perpendicular to each other. Those materials could be relevant for BCL type, kind of experiment. Now, kind of my last question is, have you thought about what happens in terms of SHG?
Good question.
Yeah, out of BCL. Yeah.
Great question. I have one immediate answer, and another one that maybe I can answer you in a couple of months because I'm studying this right now. So in a new project. So first immediate answer is I can use BCL to switch on and off SHG responses, because let's say that I start with a system that has inversion symmetry. So I don't have SHG, I don't have shift current nor injection current, right? Then I apply one of these BCL lights. Then I break inversion. And then this response becomes finite. So BCL can be used to switch on and off nonlinear responses, for example. Now, how this happens in detail, like what is the magnitude of this response and the dependence on direction, phase difference, this is what I'm calculating now. So maybe I can tell you this in more details in a couple of months.
Okay, happy to learn. When you are ready, please let me know. Thank you very much.
Sure, you're welcome.
Any other question?
I think we have something in the chat. I just see it now.
Yes, it was a couple of minutes ago. My apologies.
That's fine. Is the person who asked the question is still in the audience?
Yes, I think.
Oh, yes, I'm here. Yeah, so I'm curious about what happened if the frequency ratio is, let's say, just not an integer, but just a rational number, and what happened is this like an irrational number?
Great question. So I was briefly looking into this. I didn't do it systematically yet, but if it is irrational number, I think you approach to a limit of unpolarized light. So like if you think of the Poincaré sphere, like what you can do, for example, is, how am I going to say? So let's suppose you have two lights with frequencies that are irrational. You can map this into a path in this sphere. And the light has no net polarization because of this. You can do the same thing with BCL. So if you apply this BCL formalism for irrational frequency ratio, you have this unpolarized light. And I know that there are works, a friend of mine has a work about using this unpolarized light to drive spin liquid phase, for example. So one extension would be consider BCL as a source of this unpolarized light, BCL with these irrational numbers.
Okay.
But this is also a possible future direction. I didn't do this yet.
And what about just like a rational number? Is the physics like very similar to the integer?
Yeah.
Okay. Thank you. Thank you.
You're welcome.
Any other question? Well, if not, let's thank Tais again, and thank you very much for coming this afternoon, or the beginning of the afternoon or the evening, and enjoy your summertime. So,
Thank you. Thank you for inviting me. It was an honor.
really great.
Thank you. Bye-bye. See you.
Bye.